Dear students, in this lecture, we will be going to learn how to draw shear force and bendment diagram for a simply supported beam as shown in the diagram. Simply supported beam with overhang on both sides, and the beam is loaded with UDL, uniformly distributed load, as well as point loads both. Now you can see the diagram. In this diagram, a beam ABCDEF, that is simply supported at B and E. That means the reaction will be acting at B as well as at E, and loaded as shown, 2 point loads 20 kN and 40 kN, as well as uniformly distributed load of 30 kN per meter intensity on the span portion BC, as well as a UDL of 25 kN per meter is applied on the portion overhang portion EF. Now, first of all, as usual, we have to calculate the reactions, support reactions, and for that we consider that this beam is under static equilibrium, so that we can use the static equilibrium equations to find out the reactions. So, applying equation of static equilibrium, that is summation Fy, summation of all the vertical forces is equal to 0, and sum of the moment or summation of the moment of all the forces, all the loads about a simple support. So here we have two simple supports at B and at E. So we can take moment of all the forces either about B support or E support and make it equal to 0. So based on these two equations, we can easily work out and we can find out the reactions at both the supports, reaction at B, that is RB, and the reaction at E, that is RE. So applying the equation summation Fy is equal to 0, using the sign convention, the vertically upward force is positive and vertically downward force is negative. So when we start adding all the forces from A to F, so first of all at A, 20 kilonewton load is acting downward, so we have taken minus 20, then RB positive, then the UDL will be converted into total load, that means a concentrated load which will act at the mid of the span where load is acting. So 30 into 2, it is acting downwards, so we have taken it negative, then minus 40 kilonewton, then plus RE since it is acting vertically upward, and after that last load 25 into 1 meter length, that is 25 into 1, and it is acting downward, so we have taken it as negative. So making all equal to 0 and simplifying this equation, we are getting the equation A, that is RB plus RE is equal to 145 kilonewton. Now, since it is this equation carry two unknowns, so we need at least two equations. So second equation we can develop by taking moment about any support, simple support. So simple support here we can take about B or E. So we are taking summation of the all moment of all the forces, all the loads about B equal to 0. And the movement which is acting clockwise will be taken as positive, and movement which is acting anti-clockwise, that will be taken as negative. So this simple sign convention for movement of a force we can take. So now you can see here 20 kilonewton will be applying negative, that means anti-clockwise movement. So we have taken minus 20 into 1, then plus this 30 into 2, that will be the total UDL converted into concentrated load, which will act at the mid of the BC, that is BC is 2 meters, so it will be acting at a 1 meter distance from B. So we have multiplied first of all 30 into 2 is the total load into 1, then plus 40 into it is acting at a distance of 3 meters, so 40 into 3, then minus this RE reaction, this will apply anti-clockwise movement, so we have taken it as negative. So minus RE into distance from B is 4, and last one is UDL, that is on EF. So UDL intensity is 25 kilonewton per meter, so total UDL, total load due to UDL will be 25 into 1, and it will act at mid of the EF portion. So total distance of this application load application will be 2 plus 1 plus 3, that is in 4, and half a meter of EF, that is 4.5. So after solving this equation, we are getting RE is equal to 68.125 kilonewton. And solving both the equations, we can easily find out that reaction at B, simple support, will be 76.875 kilonewton, and the reaction at E will be 68.125 kilonewton. Now in the here we have calculated the reaction, so now we will be developing the equations for shear force. So for shear force, we can take a section and with at appropriate location. So maximum possible reaction sections we can take. First of all, we can take section between EF, then another section we will take between ED because load pattern is changing, and after that we will take section between CD, or we can say DC, and fourth will be between CB, and the last one will be between BA. So first of all, let us take section XX at a distance X from the end FB of the beam as shown in. Now you can see the section. This is the section. So section we have taken XX section at a distance that is X meter. So this distance will be X meter. Usual we take this as X meter distance. So this is X. Now we have to calculate the shear force, and as per the definition of shear force at a section can be calculated by taking the algebraic sum of all the forces either on the left side of section or on the right side of section with the specific sign convention which we have taken and we have discussed in the previous numericals also. So first of all, we are taking section between F and E, and the shear force equation, only one load is acting, 25 kilonewton per meter, and it will be acting on X length. So it will be total force will be 25 into X kilonewton. So that we have written here. And since this equation has maximum degree of X, maximum power of X as 1, so it will be a first degree equation, and we know that it will be the straight line. Straight line mean it may be either inclined line depending upon the equation. Now since okay, and we can calculate shear force at the extremities, that means section at point F, that means at section F as well as E, because this equation is valid only between E and F. After that another load will come into practice. So taking distance X equal to 0, shear force at F will be 0, and the shear force at E, here we will be taking just right of E, and right of E, then it will be 1 meter distance, so 25 into 1, put here 1 meter, 25. So both the shear force we have calculated, shear force at F as well as shear force at E. And the shear force, when you take just left of the E portion, that is section E, when you take just left of E, then this RE you need to taken into calculation. So it is plus 25 minus RE. So it will be, when put the value, RE is equal to 68.125, which we have already calculated. So ultimately we are getting shear force just left of E is equal to minus 43.125. Now when we have to draw the diagram, then what will be the diagram of the shear force between F and E? It will be an inclined line. Why inclined line? Because load is a UDL. So UDL, when loading is of a uniformly distributed type, then the shear force between those points, it will be, or those sections will be an inclined line. So inclined line, that means it is varying from 0 to 25 kilonewton. So that we have written here. Yeah. But after that, just at when you take the value just left of E, that means somewhere here, so there you are finding vertical load is acting, that reaction is acting. So whenever there is any vertical load acting, that means point load, concentrated, or you can say concentrated load, then there will be either drop or rise in the vertical rise or vertical fall in the shear force value. So here we can see that shear force just right of ease was 25 positive, and after that due to reaction it dropped to negative value minus 43.125, which we can draw like this. So here we can say now here this will be the reference line. So 0 to 225 positive, then minus 43.125 kilonewton negative. Now between we have to develop the equation for the shear force between ED. So we have taken section which is section XX at a distance x, again x, from the free end, that is F end. So this will be the way how to develop the shear force. Shear force will be 25 into 1 at this section. So that means 25 into 1 will be the total load due to UDL, and after that minus 68.125. Only two type of forces are acting in the right side of the section. XX 25 into 1, that will be the total, and it does not depend upon the now x distance is this one, and RE, which is acting vertically upward. So shear force at E, which is minus 43.125, which we have already calculated. And now you can see here from E to D, there is no load. So no extra load is acting. That means shear force will remain constant between E and D. And we can draw the horizontal line minus 43.125 kilonewton. And when we talk about shear force at D, so just in the right of D, it will be minus 43.125, and which we have calculated here. And when you take just left of D, then this 40 kilonewton load will be also need to be calculated, will be taken into consideration. So plus 43, then minus 3.125. So that means we have calculated shear force at D. It comes to be just right of D. It is 43.125 kilonewton, which we have already drawn. And just left of D, it will be minus 3.125. Now again, equation is again here uh, constant value. That means constant between shear force at E and D, and after that there is variation. And as already we have discussed, that whenever there is a concentrated load, either vertically downward or vertical upward, so there will be directly variation in the shear force in the vertically upward or vertically downward. That means maybe from positive to negative, etc. So shear force even at C, just right of C, if we calculate, then again it will be minus 3.125. So it will be remaining, shear force will be constant between D and C. So first of all, we have written the 3 points. That is, first point is straight line. Shear force diagram will be straight line between E and just right of D, which we have drawn. Then second is a vertical rise at D. Vertical rise at D due to downward load, and its value will be increasing from minus 43.125 to minus 3.125. And so we can see here that this value at D increased from minus 43.125 to 3.125, and after that it will remain constant, so it will be a horizontal line between DC. Now another equation, shear force equation between C and B, when we have taken the section between CB. So quickly we can solve it, that sum of all the forces, first of all 25 into 1, then minus 68.125 RE, then plus 40, and then some portion of the UDL just in the right of the section, so from between the section and C point. So if total distance we have taken x, then this distance from C to section will be x minus 3, x 1, 2, 3. So that's why we have taken x minus 3. So you can easily understand here, again it is a first degree equation, and so accordingly we have to draw the diagram. Now, since it is a UDL is acting, so and the equation is a 1 degree, so that means shear force diagram will be an inclined line. So first of all, shear force at B we can calculate by putting the value of x equal to 2 plus 1 plus 1 plus 1, that means 5 meters. So when we put the value of x is equal to 5 meter, we are getting shear force 56.875 positive value. And shear force just left of V when we have to calculate, then this RV reaction you have to take into consideration, which was 76.875. So ultimately you are getting minus 20 kilo Newton. So shear force just right of B is plus 56.875, and just left of B it is minus 20. And you can understand that beyond B and A there is no load, so shear force will remain constant, and after that there is a drop 20 kilonewton, so there will be a vertically change in the shear force diagram. So shear force at A will be minus 20. So shear force will be inclined line between C and B because there is uniformly distributed load, and vertical drop from 56.875 positive to minus 20, and a constant shear force between B and A. So this will be the diagram here we can draw. Now bending moment equation. So again, similar to shear force, we are taking a different type of section. So first section is between EF, and similarly there are various types of section we can take. So directly switching over to the equation for the portion FE. So shear, now here we have to calculate the bending moment. So bending moment at a section, as per the definition part, it is the sum of all the moment of all the forces either on the left hand side of section or right hand side of section with respect to the section which we have taken. So here bending moment will be when we take section at XX between E and F, then this much load is acting on the span of the portion of the span which we have taken into consideration, and intensity is 25 kilonewton per meter and span is x meter. So 25 into x, that will be the total load due to UDL, and it will be acting at the mid, that means x by 2. So we have taken 25 into x by 2, since it will be giving a hogging type of movement, so it will be taken as a negative. You are well aware in the previous numerical we have discussed it also, that whenever there is a hogging movement, then it will be taken as negative. If it is a sagging one, then it will be taken as positive. So we have taken here negative. And it is an equation of second degree of x. So it will be parabolic curve we have to draw between F and E. So first of all, bending moment at F, that will be 0, and bending moment E, you have to put in the equation x equal to 1. So we are getting minus 12.5 kilonewton meter. So variation of the curve, or draw the curve between 0 and minus 12.5, it is a parabolic curve. So this is the way how to draw 0 at the F point and minus 12.5 kilonewton meter at E. Now, next section we will be taking between E and D, and bending moment equation. It will be again 25 into 1. That 25 into 1. This is the UDL, and distance of net force due to UDL from with respect to x-axis, which we have taken into consideration. So total distance is x, and half we can subtract, so that is x minus 0.5. That means it is acting somewhere here, so half we have taken into consideration. Second concentrated load, that means reaction 68.125. Now this 68.125 will be giving a sagging moment, so we have taken it as a positive, and it is acting at a distance x minus 1 from x-axis. So this is the way how we have to develop the equation for the bending moment, and since it is a maximum degree of x is 1, variable is 1, so it is a straight line between E and D. and bending moment at E will be minus 12.5 by putting the values, and bending moment at D you have to put the value x is equal to 2. So we are getting bending moment E is equal to minus 12.5 kilonewton meter and bending moment at D plus 30.625 kilonewton. So this is the way we can draw the diagram. It is a straight line diagram. However, it will be inclined because it is moving from minus 12.5 to plus 30.625. Now next section we have to take between D and C. So bending moment equation, this portion is remaining same. Now 40 comes into picture. So 40, it will be giving a hogging moment. So 40 into x minus 2. So by putting the values, we are getting bending moment at C is equal to plus 33.75. Then we can take the section between C and B. So similar to the previous part, we can develop the equation. Now 25 into 1 into x minus 0.5, then 68.125 into x minus 1, same 40 into x minus 2. Only this much component will be added. So this, when you take section somewhere here, this is a distance, this distance will be x. So only this much portion of the UDL you need to take into consideration, and it will be giving a hogging type of movement, so we have taken negative. So 30 into this distance, this is total distance is x minus 3 will come into picture, and it will be acting at the mid of the span. So x minus 3, again we are multiplying it with x minus 3 divided by 2. So it is a second degree equation, and we know that if it's second degree equation, then it will be parabolic part. So bending moment B will be minus 20 kilonewton meter. When you put the value of x in the above equation, that x will be 2 plus 1 plus 1 plus 1, that means 5. And the bending moment A is 0 since it is a free end, and the diagram between B and A for bending moment will be straight line. So this is the way we can draw. Here this is a straight line, that means inclined line, and this is parabolic equation, and this last one is inclined line. Thank you.